The right thing is to say fire at will, and hopefully will duck. So, all right.
Okay, we see you recording. Good. Okay, well, good evening. Welcome to the Texas DX Society's March 2021 monthly meeting. I'm Doug, W9LCQ. I'm the Texas DX Society Secretary, and I'm hosting this meeting. Before we launch into the program for tonight, I do want to acknowledge the slim pickings up there on the screen. There we go. Yeah, Jeff Greer, W5JEF. How about that? From Richmond is our member number 234. He just joined this week. So congratulations and welcome aboard.
Welcome aboard.
Yeah, welcome, Doug.
Thank you very much.
Jeff.
Okay. And without further ado, I'll turn it over to Roby for his program on the Smith chart and overview. Now, Roby Elms is AJ4F, and he's our past president for the Texas DX Society. Now, I want to remind you all to mute your microphone unless you're going to ask a question. Take it away, Roby.
Okay, here we go. All right, so this, I have a little slide pack. Is it visible to you guys?
Absolutely.
Okay, so I've called this the Smith chart and overview. I was asked to put together something to talk about Smith charts, and this is an incredibly complex topic. The chart is pretty complex, but the whole topic that it deals with is very complex. So I have built a target, little presentation tonight just to make sure everybody is aware of the basic devices we're talking about and what the circuit and what the parameters are, those sort of things. So this is sort of a middle of the road presentation. The Smith chart is a little bit difficult to show on the computer screen, but I'm going to do it anyway for a little while. And then I'm going to switch to a piece of software called SimSmith and demonstrate some things with SimSmith. And it's the way to use the Smith chart today. So it's pretty interesting. Let's see, my objectives tonight. So I'm going to try to help you develop begin developing an intuitive understanding of basic RF systems that are used by hams. And I'm going to identify a circuit model that will be used for that understanding. And then I'm going to identify what parameters that you need to have in order to analyze the system. And then I'm going to expose you to 3 different ways to do it. 2 of them do not require higher level math skills. One, I'm going to show you some of the equations involved and talk a little bit about that, but only a few minutes. I'm going to introduce you to the Smith chart itself, which is a graphical, it's basically a plot of the complex reflection coefficient between a load and a transmission line. It's also a nomogram that's used to solve the equations graphically. And it was used, and I'll talk a little bit about its history in a minute, but introduce you to that approach, and then talk a little bit about some of the pluses and minuses of that approach. And then I'm going to shift over to SimSmith, and I'll introduce you to SimSmith, and then I'll work a couple of examples for you, which I think will accomplish the goal of helping you to start to develop an understanding of these RF systems. So what are we talking about? So in the simplest, the way I chose to do this tonight is to look at a system that we all use. We have some sort of an antenna connected by some sort of transmission line, typically coax, but doesn't have to be, to some sort of a radio, some sort of a rig, some sort of a transmitter of some kind. So what we're going to be looking at is what are the values of impedance, current, voltage, that sort of thing in this transmission line between the rig and the antenna. And all of this depends on the power levels, the impedance of the antenna, the length of the transmission line, the type of transmission line, you know, that sort of thing. Okay, so here's the model that we want to use, and I'll kind of maybe switch back and forth between these. So the antenna in the little picture that I had there a minute ago, you have to represent that by some circuit elements. So it's represented by a resistor, in series with an inductor, in series with a capacitor. The transmission line is just 2 conductors, can be more, but the ones we use are 2. And it has certain parameters as well. It has a physical length in feet. It has a velocity factor. In other words, how fast do the radio waves travel down the wire? It has an electrical length, which is different from its physical length. And it has some sort of loss characteristics we generally refer to as attenuation. So if you look at your spec sheet on a piece of coax, it'll tell you something like 0.9 dB per 100 feet or something like that. But it has a loss, and it has a characteristic impedance. And the coax that we use is typically 50 ohms, and it doesn't have to be the 75. There's a lot of various impedances. There are also other options, you know, a 450 ohm open wire line and the like. Somebody's running a fan or something. That's me. But you need to know those parameters in order to answer the questions we're talking about. And then the radio itself, in the RF world, is typically called a generator, but it's something to produce the voltage, and it has an internal resistance. And we typically, our equipment is typically designed to have a 50 ohm internal resistance. Doesn't have to be, but that's what we have. And then the voltage is what is changed in order to drive the power. So that's kind of the circuit model. So these devices all have to have values. Resistance of an antenna is determined by its physical length and the material it's constructed of. The configuration of the antenna determines its length determine its inductive reactance, which is this X sub L. And that can, if you know the value in ohms of inductive reactance, you can calculate the actual inductance of the antenna at a given frequency. That's what this little formula is. The capacitive reactance is determined by, again, the configuration of the antenna, its physical properties, physical location above ground, and that sort of thing. And you can solve for the capacitance given the frequency and with the inductance that you can measure. These reactances of inductance and capacitance are opposite in sign, so they subtract from one another. So you won't see an antenna with it as I have drawn here. You'll see it is R plus or minus X, and the plus or minus will be determined by which is the X larger, or is the C, or the X sub C larger, or is the X sub L larger. So the two are just the arithmetic average. You guys have heard of impedance. Well, impedance is an interesting number. It's a complex number. And here's how you determine impedance if you know the reactances and you know the resistance. So you take the square root of the sum of the squares of the two numbers, and then it has a what's known as an angle. Since it's a complex number, it has both a real part and an imaginary part. And you take the tangent of that, the inverse tangent of that fraction, and it gives you an angle. So an impedance will have a number like 50 at 20 degrees, or 50 at 0 degrees, or 50 at 100 degrees, or 300 at 40 degrees, or something like that. And with that information about the angle, I can tell you how much is resistance and how much is reactive, and I can tell you whether that reactive part is inductive or capacitive. The physical wavelength, the physical length of the electrical length of an antenna is related to its physical length, the frequency at which you're operating it, and the velocity factor of the transmission line. The velocity factor is determined by the materials of construction of the antenna, or excuse me, of the transmission line. A open wire line with almost no spacers in between the two conductors has a velocity factor of up in the 0.9, middle 0.9 range. A typical coax with a solid polyethylene dielectric has a velocity factor of about 0.66. And so the velocity factors that we deal with are typically in between those values. So what we're going to be doing in order to understand what the SWR is, understand what the impedances are, how much voltage is transmitted or power is transmitted, those things, we have to convert the picture, the physical situation, into a picture like this. So have I lost anybody? Anybody got any questions? Have I made it clear? Okay, we'll keep muddling on then. So if you have these values that I'm referring to, and you need another couple, I gave you some equations already. I gave you another equation. Here's another equation. It's called the transmission line equation. And what it does, let's go back here a minute. Let's see. In my little diagram here, if you can imagine yourself looking in the transmission line at the radio toward the antenna, that we're going to call Zn. And this equation tells you the value of Zn as a function of the length of the line. So in other words, if you're at the very end of the line next to the rig, you will see some value. And as you move toward the antenna, moving up that line, that value will change until you get to the antenna, and you will have another value there. So the length of the transmission line is important in determining what impedance the radio sees. If we have a number of these parameters, we can solve for the ones we don't have. And if we have the voltage coming out of the generator, we can calculate powers, we can calculate voltages and currents and that sort of thing. So we're turning this radio system into an electrical model in order to come up with the values, is basically what we're doing. And again, I'll call your attention to this. This is called complex algebra for a couple of reasons. Number one, even without the reactive part, it is rather complicated and tedious, but these numbers, as I said, are called complex numbers because they have a real part and they have an imaginary part. In the electrical world, since the operator I, or the variable I, is already taken for current, we chose to use the variable, the operator J in order to indicate the reactive part. So if you show this equation to a mathematician, they'll ask you what J is, and they'll replace it with I, since mathematicians don't use the J. So that's just part of the math that's involved in coming up with these numbers. One way to solve, to see what these impedances are, is what I call the hard way. And that's just the analysis of it, just by doing the math. So you have to manipulate all those equations to put them in a form so you can solve for the variable that you're interested in. In other words, what number are you interested? Are you looking at impedance? Are you looking at SWR? Are you looking at length of the line or whatever? You plug in the other numbers and you can derive that. So you manipulate the equation, then you have to solve the equation in order to get the value that you're looking for. Now, this process is tedious. It's error prone. It is usually you have to do it several times in order to get. It's usually one value is not what you're looking for. You're looking for a range of values. So you usually have to solve it multiple times, and then you've got to figure out some way to show what to show the data in a meaningful way to help you understand what you're looking for. Because what we're trying to do is develop an understanding of what's happening in addition to getting the values. Complex algebra is, like I said, is tedious. So you'd end up writing, you'd either end up doing by hand or writing a spreadsheet, putting in multiple equations in the spreadsheet or something like that. But in any case, it would take you quite a while to do. The Smith chart. So this analysis that I'm talking about, this system that I was talking about, is developed in, many years ago whenever radio first started. And then the 1930s were really the golden age of this developing of a mathematical understanding of this system we have. Bell Labs was sort of at the forefront of that, and they were working to develop at that time, point-to-point communication systems. They were working to develop ways of operating at higher frequencies. And if you know much about the history of ham radio, you know that hams were all a part of that. But because of the difficulty in solving this equation to come up with these numbers, at Bell Labs, this guy named Philip Smith designed the Smith chart, or what became known as the Smith chart, because it allows you to solve most of the problems that you're looking for in this system with a graph, rather than having to do it strictly by solving all the equations. So the Smith chart is designed in such a way that it displays the data in a relatively meaningful way. You can do the calculations by just drawing lines on the graph. However, you do have to plot it. The graph is a plotted sheet of paper. So you have to plot the data on the graph, and you have to use drafting tools in order to basically measure and do the movement of the data on the graph. You're going to be drawing circles, drawing straight lines, and that sort of thing. So you're going to be using a compass and a straight edge that helps you come up with what the values are. I don't know if you guys have ever used a nomogram before, but many years ago they were quite popular, where you had them in a line, and you took a straight edge, and you lined up various variables on the straight edge, and it gave you the answer on another line further down on the page. This is a little more complicated than that, but it's still the basic kind of thing that we're talking about. So here's the Smith chart. It's got a lot of data on it. Really, it does. Where's my mouse? There's my mouse. It doesn't do very well on the graph. Okay, so this chart, which I will go into in a little, I think I'll just go ahead and go into it, but around the circumference of the chart is the length of the transmission line, both to the load and away from the load. Down here on the bottom are these straight lines called radical parameters, where you drop a line down from the graph straight onto this, and you can read things like SWR, you can read things like reflection coefficient, loss factors, any of those number of those parameters. So that's the Smith chart. So you were using this. Just one other thing, the red lines have to do with impedances, and the blue lines have to do with admittances. So what's an admittance? Admittance is 1 over the impedance, and that's why they're on opposite sides of the graph, and both right, left, top, and bottom, even though it's not, with this one, it's a little bit hard to see. And we won't talk too much about admittances tonight. I think we'll use them in one spot. But anyway, that's what the Smith chart looks like. So you can see there's lots of lines on this thing. It's still kind of complicated to use, but it's better, it's faster than doing the numbers. So I borrowed this set of graphs from this set of slides to talk about a little bit more about the Smith chart. These are from one of the ARRL technical directors. His name is in my credits at the end, but he did a fairly good job of it. So what is a Smith chart? It's a graphical tool to plot and compute complex impedance, complex reflection coefficient, standing wave ratio, transmission line effects. You can do solve matching. You can do matching on it, and you can do a lot more. The Smith chart is a powerful tool. And as you can see, his example of the Smith chart here is the one that includes impedances, and he does not show the reactances. So they're just, you can buy these charts printed any way you want them, or print them any way you want them this day and age. Another thing that this chart is the way this chart works the physical chart is that everything is a normalized value. In other words, the very center of the chart, the very center of the chart, show up here in a minute, right here, it has the value of 1. So in order to do that, you take the actual impedance that you're going to work with and you divide it by your system impedance. The system impedance for us is typically 50 ohms. So this is an example. So if you have an impedance that's 37 plus J55, to normalize it, to make it what's called in the Smith chart world Z prime, you divide 37 by 50 and you divide 55 by 50. So the region on the Smith chart, the line, the heavy black line that goes right down, or the line that goes down the center that he's made heavy in blue here.
Roby,
Yes.
Roby, we missed you about 30
yeah,
seconds.
you said, yeah, we missed you. You were doing the second division by 50. That's where you hung up.
Okay, am I back?
Yes, obviously.
Okay, all right, so let's go back. So the second division by 50 here from 55 over 50 gives you the fractions 0.7 plus J110. And these are the values that you're actually going to plot on the Smith chart. And we'll be doing that in a minute. So here are the regions of the Smith chart. The line, that horizontal line in the middle, is your axes of pure resistance. So you have no reactance on when you're on that line. If you are below the line, you react on these curves that you're inductive. If you're above, you're capacitive. If you're above the line, you're inductive. And that's what positive J, JX and minus JX reveals or tells you. So the key values on the chart, on the right-hand side here, it would be essentially an open circuit. In the middle would be your characteristic impedance, or if you're using it as a fraction, would be 1. So let's say our characteristic impedance is 50. So we divide 50 by 50, we get 1. Okay, so that plot's in the center. Right, my mouse, this does not a good job. You can see it right there. That's 1. Okay, a short circuit or 0 ohms is over here, and infinite ohms is over here. Now, maybe one thing you can already begin to see is either very large numbers or very small numbers get very difficult to use with a Smith chart, because you're going to have to read the stuff off this graph. Okay, so you're going to have circles whose center is drawn on this horizontal line. And when you draw a circle centered there, it's going to be a circle of constant resistance. You're going to have anywhere along that circle, you're going to have a value. In this case, here I'm on R prime equals 1. You're going to have a value of R of 1, or in the real world, you're going to have a value of 50, right? You have to go back and forth between those two. So the circles that are drawn with this edge, with the tangent to this edge, and with the center up here somewhere, are constant reactance circles. And this is an inductive reactance circle with a value of 1 in the normalized world, 1 in the real world, 50, since we've chosen the 50 ohm impedance as our system impedance. And here is the curve that goes down. That's negative J1. If we put that in the into the real world, that's 50 ohms of capacitive reactance. Now, if you want to know how many picofarads or microfarads or henries or millihenries of inductance or capacitance it takes to get those values of 50 ohms or of capacitive reactance or whatever, you go back to those formulas that I showed you to start with, the 1 over 2 pi FC or the XL equals 2 pi FL. Those are the frequencies that you use. And the number, the XL is in ohms, the frequency is in hertz, the inductance is in henries, the capacitance is in farads. You know, it's just, you just plug it in and solve it to get the value. So to do this work, you have to be able to work in both the normalized world, and then you have to work in the real world, because you're doing this to build something. And to build something, I don't want 40 ohms of reactance because I can't buy that. What I need is I need a certain amount of inductance or a certain amount of capacitance or a certain amount of resistance. Those are things that I can, you know, I can get, you know, that I can produce. Like if you ever looked in the catalog, you won't find a capacitor with 50 ohms of reactance. You'll find a 0.01 picofarad capacitor or 33 picofarad capacitor or something like that. So this is how you translate between the mathematical world and the physical world. So to plot this point, which is a little bit different one we started out with. So we start out with the Z of 25 plus J40. We divide by 50 to normalize it. So we come up with a half, 50 over 25 over 50. And here's our half circle right here, our constant resistance circle going in this direction. And then we have a 0.8 for the inductive reactance. And here's the 0.8 circle. So that value, that blue dot there, is the impedance of 25.J40. But since we're doing it in a normalized system, it's 0.5 plus J.08. So that's what we're doing. We've put that impedance on this graph. Now, if we plot that particular value of impedance, and you'll see this in my examples later much better, and then we go to the prime center of this chart, which is let me find it. My little cursor just does, once it goes over this page, just doesn't do very well. If we put our compass in this at this point, and then we draw and we expand the compass to reach our plotted point here, and we draw a circle of that radius around the center point. This is our SWR circle. This is a constant standing wave ratio around this circle. And with those radical parameters in the past, if you want to know the value, you can drop a line perpendicular to or tangent to this blue circle, the edge, and right down to that those radical parameters, and you can read off the standing wave ratio. The other thing we'll demonstrate that this talks about here is along the transmission line, when you're moving toward the from the load toward the generator, or from the generator toward the load, the impedance that you will see changes as a function of how far you are from that point. And what this shows is that if you this one full circle around the Smith chart is a half wavelength. So if we start out with an impedance of up here of, say, whatever that number we gave was, a half 0.5 plus J.8, and we go all the way around to the same place again, we will see the impedance, the same impedance. And one thing you've heard, taught in the ham license stuff, license instructions and that sort of thing, is that impedances repeat on a half wave on the length of a transmission line. That's what this talks about. A quarter way around, or halfway around the Smith chart, you get sort of an inversion. So if you've got a really high impedance over here, if you have a large SWR circle, and you get, and you're over here somewhere and you draw your SWR circle, if you have a quarter wavelength at the frequency that we're talking about here, it'll put you over here on the other side of the chart where the numbers are very small. So that's one thing I've heard people talk about. Sometimes you need to be wary of a quarter of the length of a transmission line. So if your load is not perfectly matched and you have a quarter of a wavelength or an odd multiple over a quarter of a wavelength line, you can get this impedance transformation, which can make it difficult for your rig to accept power.
And again, the visualization here is you're traveling down this transmission line. You're seeing the impedance change as you go down through the transmission line.
That is correct. Okay, so here's a little bit more impact. This talks about what you've measured at the antenna or measured at the transmitter, and if you move down the transmission line this way, it gets closer and closer, or it changes. And as you get close to the antenna, you will see. I mean, if you get to the end where the antenna is, you can actually see what the impedance of the antenna is based on the impedance that you see that where the transmission line is connected to the transmitter. And I'm gonna work one of those examples with a Smith chart. Too hard to do with these charts and the like, and particularly with the numbers. Does that help? You kind of see this? I lost anybody?
Yeah, that explains why you sometimes have to add or subtract on the feed line.
Exactly. Interestingly, if you have a perfectly matched line and perfectly matched line to the load, it doesn't matter how long the line is. And we'll see that again. We'll see that in one of the examples we try to work. This is just another kind of version of that. From another, I thought it might show it a different way. It might show a little bit different. And maybe sometimes you can, my words will help you understand where somebody else's words won't, and vice versa. So we're talking the same language here. Here we are, the transmission line. We're looking at the load. Here is L, the length from the beginning of the transmission line. And then as we move toward the source, we move toward the source is starting at the load and moving back toward the generator or the source of power. Or if we start it, or we can move toward the load, which is kind of, think about it starting at the source of power and moving toward the load. So there's just two different ways to go. So the pluses and minuses of the Smith chart, a real minus in my mind is large and small numbers are really hard to work with due to the limited number of lines on the chart, which means you've got to do a lot of interpolation and a lot of guessing as to exactly what it is. It makes it difficult. A positive, it's relatively fast. Once you learn and get proficient at it, it's pretty good. The other thing I think that's really good about the Smith chart, it helps you visualize, if you can accept that this point that we're looking at is the impedance at a specific point, and as we move around the circumference of the chart, we're changing the length of the transmission line. You get a really good feel for how the system behaves. So I'm going to now change, and I've got another slide or two here, and then I'm going to actually run SimSmith and show you some of these things, which I think will be a lot more meaningful. SimSmith is a program. It's written in Java or JavaScript. It runs on Windows, and it was developed by AE6TY, Ward Harriman. There's his website. This mimics the graphical methods used by the Smith chart to display information and to solve problems. And it uses all the equations that we have talked about at a very high level earlier to develop precise values. This is a tremendous program. It does all the heavy lifting, all the calculations, and it provides data display in a very usable format. And for its cost, its value is infinite. It's free. You just have to download it and
You did it again, Roby.
Lost your audio, Robbie.
Dude.
Anybody know any good jokes?
He can't hear us if we can't hear him.
Right.
am I back?
Yes, you're back. You lost. You were talking about downloading the SimSmith software.
Okay.
No, lost.
Oh, okay. Here we go. Okay. Is it still, it's there now?
Yes.
Okay. So SimSmith you download. What I'm going to do is I'm going to run it here in a second. I'm going to show you navigation. I'm going to show you preferences, which is how you change the display to get some of the things you want to use and make it look better, make it more useful for you. We're going to talk about plotting impedances. We're going to look at transmission line effects. We're going to look at half and quarter wave line properties. We're going to look at the impact of SWR of line length on SWR in the no loss case and in the lossy case, which is, I think you'll find very interesting. And we're also going to do a little bit of impedance matching. Okie dokie. So let's see, stop sharing this. And then I'm going to start sharing SimSmith. Okay, can you see SimSmith?
Yes.
Okay, so this is the program. This is its user interface. And starting up here in the upper left-hand corner, it's the same model that I drew before. You have a generator, you have a source of some kind with a resistance, you have some type of transmission line, and you have a load. What's different here is that you put in your values in these blocks and it plots them on the chart for you. So for instance, I have 50 ohms with no reactance. This is resistance. This is in reactance. So I have 50 ohms, and look, right in the middle of my chart, I have my plot. I have my Z, I have my value put in. So let's just for example, let's change this. It's kind of dark. So now we moved over to 75. The little red dot here. So here's 75. See, and I told you that going to the right was increasing resistance values. Okay, so we moved from 50, we moved over to 75. Now I might add that with SimSmith, you can use real values. You don't have to go to
Oops, I think we lost them all together.
Okay, am I back?
Yes.
Okay. I think where I was talking about here's 75 ohms. So let's make it even bigger.
We lost you as you were saying you can use real values. We didn't hear anything after that.
So with SimSmith, you can use real values. You do not have to use the normalized business like I showed you with the graphs before. So I made R100. So now I've moved to 100. And I got to do something here. Just give me just a second so I can see a little bit better on my keyboard. Okay, I'm back. So let's just change this to 250. And you see where I put in 350, excuse me. So here's 350. We can change it to 10. And, you know, we move back over here. So we're plotting on the R, on the R graph. So let's add some reactance. We'll add 15 ohms. And now, since we added plus 15 ohms, we moved up. Remember, this is the positive, this is the inductive side of the chart. So here's 10, here's 20. We're not quite in the middle, but these charts this is not real linear. So there's our 15 ohms. So let's change this to, let's say minus 50 ohms. So down here we are here at minus 50. So this is R10, R is equal, this is 10 minus J50. This is the point that we were talking about graphing before. Is this plotting of the different impedances. So let's do something that's a little more normal to us. I'm going to make my load 75 ohms with no resistance. I mean, with no inductance or no reactance to it. Now, my transmission line here, this T1, has a value of 75 ohms. Excuse me, though. It has a characteristic impedance of 50 ohms. And these are the other parameters which you don't have to worry about because I'll show you how to pick these in a minute. But it has 0 length. So what I'm really telling you is that this point, this purple or pink point is connected to this blue one, and the T really doesn't exist because it's 0 length. So we're going to make it something other than 0. So we're going to make it 25 feet. And now look what it shows us. Here is our load. Remember, we plotted this point. Now we added 25 feet of this transmission line. It has a characteristic impedance of 50 ohms, a velocity factor of 0.66, and that moved us to here. So now you can see, here's the values. These values are looking in here. So now the resistance is not 50 ohms, it's 33.74, and the reactive value is 4.08. So, and here is our standing wave ratio. It's 1.5. So I have plotted on this graph an SWR of 2 just to put it on here. So I'm not going to lay one over top of the other. So here's how you work with SimSmith. So I'm going to change the length of the line, and you can see how this works. I'm making the line shorter, and you see the blue point is what you see, is what the generator sees. So I'm making the line shorter, and you can see it's crawling back toward the generator. And you can read the values here that are seen at this point. And of course, if I make it, we've already had it 0, but I'll make it 0 again. So I made it 5. I don't want to do that. So at 0, then the generator sees exactly the load. So these 2 points are lying right on top of one another. So now let's make it a quarter wavelength long. So we're operating at a frequency of 7.1 megahertz. We have a velocity factor of 0.66. So I could calculate by hand how long to make the transmission line, but I'm going to let the program do it for me. And a quarter wavelength is considered to be 90 degrees. The full wavelength is 360 degrees. So I'm going to plug in 90. If I could figure out how to type. So I'm going to put in 90. Now here I am exactly opposite side of the center from where I started. So this is that inversion that we talked about. So the value is 33.33 ohms, and I have no reactance. So let's make this 180 degrees to illustrate the point again. Now, I'm right back where I started. My reactance is 75. Excuse me, my resistance is 75, my reactance is 0, which is the same, you know, I'm right back on top of my point. So let's make it 720. So we're going around a bunch of times, right? And I end up right back where I started from. So that demonstrates the circularity of the repetitiveness of this transmission line. It shows you that that's the kind of thing that happens. So that's a couple of the points I wanted to demonstrate. So I'll go back and talk a little bit more about, well, while I'm here, I'm kind of changing the way I'm doing this on the fly, but this is my operational frequency. I can make this anything I want. I can make it 14 megahertz. And you see things change according to what values you put in here. So this program is very interactive. It's very interactive. It's very easy to use. Now, if we were using the Smith chart, we'd have to go back and do a lot of redrawing and that sort of thing. But with SimSmith, we just plug in the numbers. So this tells you I changed the frequency to 14 megahertz. The length went to 183 feet because I had 720 degrees here. You know, it's once I put in the basic factors, it recalculates everything for me. So I'm going to go back to something pretty sane here. I'm going to say 35 feet. Okay, so 35 feet is not quite a full wavelength on 20 meters. It's about 3/4, and that's where we end up. We got 271 degrees. And so does that, I guess I'm kind of checking for understanding here. Can you kind of see what we're doing and what kind of results we're getting? Does this sort of make sense for you?
Yeah.
Okay, so here's another couple of things to look at. So I'm using a perfect transmission line here. It says it's lossless, and that's what that's what SimSmith considers to be a perfect line, is one with no loss. It has a real velocity factor. So I'm going to change this. So when I clicked on this box, I have lots of options. And these are all, it has the data loaded into it for a lot of commonly available transmission lines. Here's the Wireman's 555. If you guys are familiar with that, that's an open wire line. It has some generic, just some basic generic lines with some basic generic parameters. It has a 75 ohm lossless line. I'm using a 50. It has your Belden family of coaxes, a number of those. And it has some that have been, whose parameters have been determined by various hams and that information given to AE6TQ, and he's loaded them into the program. So you have some there. So, you know, I have lots of things to choose from. So this, what makes this program very, very useful, is I can do real world stuff with it. So I'm not a Belden man, but but I'm going to choose 9913. And let's see here. So by simply clicking on it like that, now I have a different velocity factor. I have a different, my parameters are different. My characteristic impedance is the same. So it is, it's pretty useful. It's so you can get real world values out of it. So one thing I should do is go back to 7.1 here. Whoops. All right, let's see if I can demonstrate. All right, so in this case, you can see that the standing wave ratio, look at this up here by the generator. Remember when we had the lossless line, the standing wave ratio was 1.5, but look at this. Now, when we put a real transmission line in here, the standing ratio is not 1.5 anymore. It's 1.45. Now that difference is not great with a 35-foot line, but it's different. Now, as the line gets longer, the SWR gets better. So let's make it, say, 150 feet long. Now, look at this. Well, I made it 15,000 feet long, so let's not do that. So you can see this is no longer a circle, it's a spiral, and it gets closer and closer to the center. So what's happening here? Before we talked about, we said that transmission lines at the standing wave ratio doesn't vary along a transmission line. Now we're saying it does. Well, the difference between the two transmission lines is the loss factor. So the SWR at the load is not changed because the characteristic impedance of the impedance of the load is not changed, but the way standing wave ratio is calculated, I'm just going to stick with the voltage case, is the voltage minimum over the voltage maximum. And since the transmission line has losses at the transmitter, at the generator end up here, the voltage starts out as 1. By the time it gets to the load, it's a value less than 1. And then when the reflection occurs to come back down the line, which is what's used to determine the standing, or what standing wave ratio is, when it comes back down the line, that reflected voltage is also attenuated by the same amount that the voltage going down the line to start with. So the measurement that you make here is a false measurement. It's because the voltages are decreased by the loss in the cable. So the more lossy the cable is, the greater impact this will have on your measured standing wave ratio. But as you can see,
so why do we measure standing wave ratio?
well, it's still very useful. And it doesn't change that much if you have a relatively low loss line. If you have a line that has a really high level of loss, it'll fool you altogether. But it's just a fact. It's just something. And if you work at it this level, you see those things. And the amount of power that's I have to say, I'm not going to go down that path. This is just the way it is. This is describing more accurately what the situation is with a real world RF system than what these things that we kind of think in our mind. Standing wave ratio is still a good tool, but it's not the only tool. So if you take this to its ultimate, the best thing you can buy is the lossiest transmission line you can find. And you'll always have a good standing wave ratio. You won't work anybody, but you'll do well. You'll have good SWR.
Roby, I think the point is, that you use the tools to lower the SWR as much as you can. For a given setup, the lower SWR is better. That's really what it comes down to.
That's right. Okay.
Hey, Roby.
Sure.
Yeah.
Go ahead, Rick.
Rick W5RH. Hey, if you're saying, you measure your SWR in your shack, so to speak, at the generator, but with this tool, you can see what the SWR actually is at the antenna.
That's right.
It changes along the line, but you can say, oh, I've got 1.5 to 1 here in the shack, but using SimSmith or the Smith chart, you can say, oh, it really is, 2.5 to 1 at the antenna. So yeah, that's the benefit of this tool. One of the benefits.
Compare different transmission lines to figure out what the losses look like on each one of them. Maybe if you're trying to figure out if it's worth spending the money on the good stuff or not.
Yes, that's right.
That's another thing. You can buy very expensive line that has incredibly low loss, but again, these are really engineering problems. They're always a matter of trade-offs. And what are you willing to sacrifice? What's important to you and what's not important to you? And this is the way with a tool like this, you're able to look at it at a level of detail that allows you to have enough information to make a good trade-off. That's basically what it boils down to.
So Robbie, question.
Sir.
Mark, N5PRD.
Yes, sir.
So this is really saying that the SWR is most appropriately taken at the antenna and not at the feed point.
That is correct.
Thank you.
Well, not really. Not if you have SimSmith. You can take it anywhere you want to. You just apply it in SimSmith and you can find out what it is at the antenna.
Yeah. But the idea is, the concept is, what really determines SWR? The characteristic impedance of the transmission line versus the load at the antenna. That's really what the figure is. The rest of it, the other things that you measure, are of some significance, are indicative, but they're not the true number unless you go through some analysis like this to tell you what the real numbers are. Now, it's sometimes kind of hard to measure the standing wave ratio at the antenna, and it's sometimes kind of hard to measure the impedance at the antenna, because the antenna impedance changes. So here's an example. So let's say I've got an antenna, I've got a small beam I want to put up, and I want to know what my SWR is. I'll measure or I want to know what my impedance is. So I take my vector network analyzer that I learned how to use a few months ago, and I connect it to the antenna, but the antenna is only 10 feet off the ground, and I get a number, and I get my resistance value, I get my reactance value. That's all well and good, and I can compare that to a 50 ohm line and say, well, my real SWR is going to be about X, but the antenna impedance is not going to be those values whenever it's 50 feet in the air. It's going to have another set of values. Now, I can shinny up the tower once I get the antenna up and put my VNA right at the antenna, maybe, and that would be one way to do it. Or I can put up the antenna, connect the transmission line, and I'll show you how to make a set of measurements in the minute where you can tell what the impedance of the antenna is by measuring the impedance at what the transmission line shows you, at your transmitter. So that's one of the examples I wanted to work through.
So can you have a great impedance at the antenna, a great SWR at the antenna, have a lousy SWR at the rig?
Absolutely. Well, can it go the other way? If you have that, you probably have other problems in measuring your SWR, probably currents on your line.
Right.
Probably currents in the external common mode currents flowing on your transmission line. They're fooling your instrument.
Okay.
Yeah, the other example would be if you'd have a value of transmission line that's totally unmatched to either the rig or the antenna, and then you would start mapping impedances all over the place at one end of the transmission line or the other.
That's right. Or if you have a segment of transmission line somewhere in between those 2 points that have different impedance, that's another thing it can throw you for a loop. And sometimes if you buy coax, you buy it from Roby's radio sales here, and I tell you, this is good 50 ohm stuff. It's not. It's really some special, 100 ohm stuff that I got from a surplus sale somewhere, and you stick it in your system and it doesn't work right. And nothing's kind of working right because it's not what I told you it was. It's not what you think it is. That's the other kind of thing that can happen. Okay, so tons of examples here. I think I kind of beat. So here's one more I want to talk about here. So I'm going to make a unusual load. I'm going to say 300 ohms, and I'm going to give it some reactance. Give it some negative reactance. Didn't do it right. I'm going to change my line length to about 40 feet. Help me out here. Okay, so you can see that here's my plotted impedance of 300 minus J150. So it's capacitively reactive and it's 300 ohms. Here's my RG8 that I've used. I have 40 feet of it. And then at the end, at the transmitter is seeing this point. I didn't show this before, but this is called the splat. This little thing here, when you put it on the chart, it tells you whatever values are on the chart. It reads it for you. So I'm going to put it here, and here is my SWR of 6.226. Over here at my, it replicates this number, 6.226. Shows me my reflection coefficient. Shows me my impedance is 12.9 ohms at J38. 12.9 ohms at J38 roughly, right? 12.86 versus 37.96. That's pretty close. Okay, so this is a pretty low pretty low R value. And let's say, and this is a situation where I'm using a non-resonant antenna, and it is, I'm going to use a tuner to match it to my rig. Tuners have difficulty in general of matching real low resistances to to higher values, to 50 ohms. It causes a lot of currents to flow in the components in the transmatch and the matching system. Overheat, and you can have real problems there. So it also might be out of the range of what my tuner will match. A tuner, when you buy it, says, oh, it'll match, my tuner will match anything SWR of 10 or less. Well, that's true depending on how they measure it, but they might not be measuring it in under the conditions that you are experiencing, that you plan to use it under. So there's a lot of things that can cause the SWR to be 10, and some of them the tuner can't handle. So let's say, so I'm here at 12.86, and maybe my tuner's having trouble matching it on this band. So one thing I can do is I can add a length of transmission line to help raise this impedance value a little bit. It's not going to change my SWR very much, but maybe it'll get into the range of what my tuner will handle. So I haven't done that. I'm just going on the fly here. So if I go from what I have 40 feet, in this case, I have 40 feet. If I go to 45 feet, let's say I go to 50 feet or close to it. Let me just do it this way. So if I go to 50 feet, now look at this. My R value is 56. My X value is 109. Now my transmatch my matching box may be able to handle 56 ohms. And all I had to do is add 10 feet of coax to this situation. So I've actually done this myself. I had a non-resonant multi-band antenna that I could match on all the bands I wanted to use it on, except one. So I would come back and I would add a length of line like this to it. And it was totally experimental. And I would find a value that worked for the troublesome band. And then I would go back and recheck my other bands. And on several occasions, I found that just adding that small length of line did not substantially upset my other bands, but allow me to match on the troublesome one. And on almost all cases, I was raising that low resistance value to a higher value that my transmatch or my matching box could, or tuner, whatever you want to call it, could handle. So this is an example of the kinds of things that you can do to help you understand. Now you see the SWR decreased a little bit here, but that's because of the additional loss in the additional length of line. The real SWR up here hasn't changed at the transmission line, hasn't changed at all, but because my transmission line is lossy, what I'm seeing at my rig is going down, but it's very small. And with this piece of coax, it doesn't have the parameters in here that you can see real well. This is pretty low loss stuff. And at 7 megahertz, I probably haven't lost more than just a watt or so at most in this setup. maybe that's too generous, but I haven't lost very much. So this is an example of the kinds of things that you can do with a program like this. And you can say, okay, 10 feet's pretty good. And 10 feet of coax is not very hard to come by, right? Just cut it, put a couple of connectors on it, put a barrel in between two of them, and man, you're back in business. So this is an example of matching with line length, which you can do. Now, there is a story in QST here a few years ago of a guy who basically did his matching system for his antenna with a set of relays and different lengths of transmission line. And you can see how you could determine something like that using a tool like this. I'm not saying that's good or bad technique. I'm just saying you can do it. Also, if you notice, some vendors tell you they've got this wonderful 43-foot vertical and it works just fine on all bands, but you need 150 feet of RG213U in order for it to work well. They're doing this. They've figured this out. They know that that takes the treble band and puts it in a range so that you can match it with your wide range tuner. It's exactly the technique that they're using for you. So I'm not arguing. I'm not saying it's good or bad. I'm just trying to explain what it is. Okay.
Okay.
Robbie, question. I'm
Sure.
trying to understand what frequency we're working at since we have oh, there it is. I'm sorry.
Yeah.
Thank you.
Yeah, I haven't done a good job of explaining all these windows, but you plug in your frequency, and I keep these two the same because I want my line lengths to work out. This is really the critical one, but 7.1, if we wanted to repeat this, any frequency, as far as I know, this thing will work from nearly 0 to as many till the computer runs out of memory for numbers. Seems like it works very well. Okay, so we're going to go back and look at something you probably never, so you've seen this, you kind of see how it works. So I'm going to change things a bit and show you the perfect case. All right, so I have a 50 ohm load. I have a 50 ohm transmission line with a 50 ohm generator. Where'd my line go? It's 50 feet long, nothing happening. Well, that's because with a perfectly matched system, the value of your impedance changes very marginally along the entire length of the line. You can see here it is changing, but it's going from 50 to 49.81. It's just changing just a tiny bit. So this is the real world perfect case of a transmission line. You're just, you just don't see it. And if you could see this very carefully, if you could see this well enough, maybe I can make it bigger. It's going to draw a little circle here. Maybe I'll make it go the other way. In other words, just like we did before, you saw the impedance move around the larger circle. Well, we're just going to have a very small circle. So the perfectly matched case is not very interesting from an understanding point of view. Everything's just okay. And what is your SWR? If you use the splat here, your SWR is 1. There's just nothing to worry about. So that would be the perfect situation for you. If, and of course we've been taught that, from the time we got, from the time we got our tickets, right? It was that we wanted everything to match. Is that, so more questions or comments?
That's not matches. The rig gets match everywhere.
That's right.
Hey, Roby, can you specify this to show return loss versus SWR?
I'm down here in the splat. Rick, I think you can. I'm no pro at this, so I'm going to say yes, but I'm not going to be able to show you how.
That's fine. No, I would think so, but okay, no problem.
So we go here to preferences, and it gives us a lot of options, and I haven't studied all of these. So you guys know where I am with this. I use this program for a few simple things, and then I don't know it in depth, so I'm not a real wizard at it, but I can do a few things with it. And it is, I know enough about it to tell you that it's incredibly powerful. And if you're interested in antennas, transmission lines, and circuits in general, this is a tool that you need to have in your toolbox.
So from the figures in the lower left-hand corner, can this also handle then tuned circuits?
Say again?
The figures in the lower left-hand corner, can this also handle tuned circuits?
Okay, so let me get, so it's a good introduction, Doug. So these are circuit elements. So this is a more than just a transmission line. Sorry, this is a general ladder circuit analysis tool. A ladder circuit is things that are in one line. So I can put a capacitor in series with my load. I can put an inductor in a shunt inductor, which is, if you look at this, that's an L network, right? So that's matching. That's how you build matching networks. So you have series capacitor, shunt capacitor, series inductor, shunt inductor, series open transmission line, shunt open transmission line, series shorted transmission line. And you already know that quarter wave lines have special characteristics, and odd multiples of quarter wave lines have special characteristics, and you can make these lines any length you want. So let's put one in here. Let's do it this way. Now here's my shunt shorted transmission line, and it has a length. And see, I can change that length. I can change its characteristic impedance. I can change the value of the line that I use for its capacitance per foot and stuff like this. And this is basically a shorted stub. And this is one of the things you'd use to tune out harmonics or reduce loading on a station that is, when you have a multi-transmitter station, you put these shorted stubs in the transmission line to knock out the harmonics of the other station, the station's on lower frequency than you are in your multi-transmitter setup. So
I just recently bought a shortened 80-meter dipole, and it has, of course, a ballander and so forth in it, but it also has a 6-turn shunt that you put across the two parts of the dipole.
Mm-hmm. And I think you can adjust those, and then here you have many other things. And these function blocks down here are incredibly powerful tools. And I don't know how to use them. I haven't gotten that far in my quote unquote education. But this is rather interesting. Just by accident. Look at this. So I put in my transmission line, my shorted stub. I've got a 0 impedance. And, well, it put me out here. It didn't help me. Forget that. I won't go there. Okay. Does this help? I mean, my objective was to introduce you to a bunch of things, and I am, and I don't want to.
Well, that functionality for building L networks and pi networks and so forth is, hell, that's better than the Smith chart.
Yeah. It's cool. It's the same tool. It's just.
Oh, yeah.
So here,
yeah,
beautiful. So we got a note from Kim. It says, have a look at the May-June 2020 QEX for an article written by K8RI. He used this software to design matching network that would make his 80-meter single-side band dipole more broadband, so he can use it over the entire 3.5 megahertz band with an SWR under 2 to 1. Yep. There's lots of tools you can use here. Now you have to know a little bit more about it, of what you're trying to accomplish, than just how to use the tool, but the tool will definitely help you.
Yeah, Roby, if I may add on to that comment, the article requires you to take a vector network analyzer and pull some data off of the point where you want to match it. And it uses that information, and it's structured in, at least in the analyzer I have, which is an AA54. You have to pull it off and then turn it into what's called a touchstone file, which is a comma separated value file with the reactive elements in it. And then the SimSmith uses that to design the network for you as you interact with these modules that Doug was pointing us to down in the corner there.
Right. So if you notice right here where my cursor is, where it says none, I have no file loaded in for the antenna. Touchstone files are available. And I don't have it pointed to the right location here, but I can import touchstones files. I can import text files out of EasyNet. You know, when you run, you take EasyNet and you put in an antenna physically, and then you run the far field analysis and you run the SWR analysis. And when you run the SWR analysis, you specify certain frequencies. And there's a file that's generated by EasyNet that contains the frequency versus impedance of various points that it uses to calculate the SWR. That information can be imported into here. And let's see, I ought to do this. It can be imported here. And then you can use this function down here called sweep, which I have turned off. And you can put in this value, the same value, frequency values, and the same number of points that you have in your EasyNet file. And you can turn sweep on, and it will show you, it will put your antenna in there on any frequency between any frequency that it has impedance values for. Incredibly powerful in that respect as well. So another comment, what we got here? Okay, thank you. All right, so let's see if I can do my little example here. So I'm going to do a matching network. And here's my story. Here's my situation. And then I'll set it up here on the computer. I've got an antenna that's installed. I've got 87-foot transmission line with it. So let's go ahead and put that in. But I can't get to the antenna to measure the impedance. It's too high or whatever. So I'm going to measure it at the end of my transmission line. So I take my transmission line, or take my VNA, and I go out and I measure it at 7.1 megahertz. And I find that my antenna is 2.515 ohms resistance, and it is 4.299 ohms, and that's inductive. Okay. So, but that is here, not here. So I'm going to change this value to 0. Now this point is the same as this point, but to determine what's at the antenna, I'm going to go backwards in direction. So I'm going to make my distance minus 87 feet. And I think that's going to tell me that my antenna is actually 6.429 or thereabouts, and its reactance is minus 664 ohms. Okay, so now I know what the antenna looks like. So let's see. So I'm going to make this 0 again, just for grins. And I'm just going through this. Now I'm going to put in my real antenna values. So this was 6.429, right? Roby can never learn how to type. He'll do well. And then I said my reactance was minus 664, right? Now my transmission line here is 87 feet. So there comes out with the numbers that I had before, the 2.515 and the 4.229, right? Okay, so now I want to do a matching network. I want an so look at my SWR, it's 20. much above what even Roby would tolerate. So I'm going to put in an L network to solve that problem. So I'm going to put in a shunt inductor, and let's see. Now I'm changing the value of the inductor. And the thing I want to bring it to is, I want it, see, this is my R equals 50 circle right here. So I want to bring it here. I think that's what I want to do. Let me just skip forward this. So this is microhenries. I need microhenries here. Why does it do that? This is something I don't really understand. This thing has some, program has some quirks in it. I wanted microhenries. I didn't want. Sorry for fumbling around, guys. That's odd. Anyway, so I put in a shunt. I'm just reproducing what I did. Now I'm going to put in my, I know what it is. I put in the wrong thing. Sorry. I want to put in the series inductor because this is highly reactive, right? This capacitor, this line, this is minus 665 ohms. So I want to get rid of some of that inductance. So all right, so you see how I've moved what the impedance is along this, see how it's curled around. And I want it to, I want to get it to touch this 50 ohm line. So I'm going to make this, it's kind of touchy to do graphically, but maybe it's this 50 ohm line I want it to touch. I guess that's the one I want it to touch. Maybe not. Okay, that's pretty close. So there's 15 microhenries in series with this load at the load in front of the transmission line. And now I have moved it. The impedance at this point is 49.5 and it's J88. So this is on this circle. So if I want to get it to 50 ohms, I got to add in 88 ohms of inductive reactant. No, let's see. That's how I want to do that. So I'm going to, So I put this capacitor in and I add about 870 picofarads. And see, now I've got it. Here's my SWR circle of 2. I'm well within 2 and I'm getting close to 50. So I need to manipulate this number a little bit. Looks like I'm gonna have a hard time manipulating that number to do better. So I would argue that this is a pretty good matching system for this particular load. I have 6.24 ohms, 664 6.429 minus J664. Up here I have here's the point. So I have an SWR of looks like about 1300. Looks ridiculous, but and at the network here, I have a resistance of 49.52 ohms and a reactance of 4.5. So I've gone way down. Now at the end of the transmission line of my 87-foot transmission line, realizing my SWR here is a little bit lower than it actually is because of the loss of the line, but my SWR is below 1.2, right? And so this is a match. This is an L matching network example, even though an L matching network example of how to get to match a load to a line. You know, this is good at one frequency, right? It's good at 7.1 megahertz. Now, if you change the frequency a little bit above and below that, it won't change things very much. So let's wonder what will happen here if we do a 5 there. I think we have to do a 5 here. So you see how it's moved around. It's a little bigger, but it's still it's under 1.5 at this point. You can see it right there. So if I would use one of the other plots that this is capable, I could determine the bandwidth between what two SWR points, like between between how wide a frequency how much frequency excursion can I have and stay below 1.5 SWR or 2 SWR or whatever. So badly done, but this is an example of designing a matching network, taking VNA data from the field, taking measured lengths of the coax or the transmission line in the field, and using SimSmith to determine the actual antenna impedance, and then using SimSmith to calculate the component matching values that are required to match that load to the 50 ohm line. And that's kind of that's a really good example of what you can do. Now I stumbled through this because I haven't done this very often, but I want to show you another little trick that I learned that's really kind of cool. See this element right here? Looks kind of like a pi network or an L network. If I just grab this one and I take it up here and I put it in, boom, there it is, it's done. My network's designed. So in my network, I had, the way I did it, I had 15.63 microhenries. It has 15.22 right here. And I had shunt capacitance of 864. It has 898.6 right here. And it does a much better job because it's right on the money. But it's the same type of network, right? It's a low pass L network. Now I can do this. I can make it a high pass L network, and see the path over here is different, but the match is still pretty good. So this is incredibly powerful tool in SimSmith that does the L matching for you. So this is kind of the things I really wanted to show. I guess I'm at this point, I'm looking for questions or comments, or what else would you like to see, sort of a situation. How can I help you understand? What can I help you
Hey,
make this?
Roby,
Go ahead, Rick.
yeah, on your fields, like you know, on your frequency field, 7.15 megahertz.
Mhm.
Can you? How do you change that number? You don't just type it in. Can you hit the up and down key and have it go to
Yes,
7?
you can use your mouse.
Yeah.
You can use the roller on your mouse and see how I'm changing.
Yeah. Okay.
Yeah.
Yeah, that's really nice. And
Yeah,
the nice thing is that as soon as one thing changes, it recalculates. That's beautiful.
That's correct.
Yeah. Okay.
And
Thank you.
see, the same thing for length. Now, a couple other things along that line. I showed you the transmission lines. There's a SCAD of them in here. There's also ways to input your own if you make your own measurements and you have the data to put in. But this is a really wide selection of transmission lines. And there are more that are available, I'm sure. Now there's different kind of generators you can use. I've used the simplest kind, and I haven't studied this much, but I know there's many of them. So if you have, see, here's a Thevenin equivalent generator, which is of another type. There's fixed voltage. There's ones that track one another. Probably the most powerful feature is to use these impedance files that you can import, and then you can do plots over ranges of frequencies. You can do many tools. You can do many things like that will help you optimize. You know, if the question is, well, what's the best, or how do I optimize my SWR over the frequency range of interest? There's things that you can do like that. This will also do filters. It will do transformers. It's capable, man.
Robbie, for a new ham like myself, my takeaway is that that throwing up a dipole or throwing up any antenna can always be improved by use of a tool like this, and also having purchased a VNA, I'm kind of wondering. You know, you take these readings. I've noticed with my VNA, I have to be very, very careful with it and calibrate it just before I use it, and it's pretty persnickety. So I'm wondering how much QRM is going to interfere with us getting decent numbers to use in this program.
Okay, so that's the real. The real issue that in the engineering and field world that I am familiar with, there are so many things that impact really accurate measurements, and then going back and choosing the right model and the right precision to use in calculating your answers is the real art of this. I will tell you this, it's been my experience that if you have, that with a little experience and a little practice, you can get numbers that are good enough to do reasonable work. Calibrate your VNA, use a very short length of line between your VNA, because between your VNA and your load. So remember what I showed you here about the impact. So you now understand the impact that transmission line has on your measurement, right? So let's say you calibrate your VNA with your load open and short right on the VNA, and you add 2 feet of line. Well, everything that you measure at the connector of the VNA should be accurate But if you put that 2 feet of line in it, then the numbers you get at the VNA are not the same as the numbers of the actual load. And we just demonstrated that here. So a better tool would be to put do your calibration loads at the end of your little small line from your VNA to what you're going to measure with. That's not always easy to do, but it's that kind of thing. It helps you learn how to make a better measurement. Also, if you get measurements that are flaky, that seem to change if you move, or or somebody walks up behind you, or if you lay something down, you better be suspicious of a number like that. There's probably something interfering with you, and it's kind of difficult to figure out what. That's not always the case, but it is. But I would be suspicious of those. The other thing I would offer for a new guy is start with something simple and work up to the complex stuff. Measure your antenna impedance, check your SWR, do some things like this. When you install a piece of coax, measure the length of it before you put it up as accurately as you can, and keep a record of what coax you have. It's just RG8 doesn't mean much. Belden 9913 RG8U means a lot more. You have to specify that. Also keep in mind that there's variability in everything we've talked about here. If you look at the specs on a piece of coax, it's 50 ohms plus or minus. And that plus or minus depends on the quality of the raw materials that are used to manufacture the cable. And I spent 30 years manufacturing polyethylene, and I can tell you that every rail car that rolled out of that plant, there's a lot of variability in the quality, in the physical characteristics, not necessarily the quality of that plastic. And that plastic is used in transmission lines, and that's the kind of thing that makes the impedance vary. So also experiment, try some things. You might try just building a few antennas, a short dipole, for instance. Experiment with it and see what you get. Something that's maybe just junk, that you can that you might not actually end up using. It might be just, might be an experiment for you. Those are the kinds of things that I would. And ask questions. There's a lot of us old geezers around that are willing to, with or without a, we'll give you an opinion. It's not work, just remember what you paid for it, but we'll try. We'll do our best to help you.
I've got a question.
Okay.
It's Keith at M5G. I've got an OCF dipole. It's a Buckmaster.
Uh-huh.
It works 160 through 6 meters. And I'm running an amplifier into it. It's a 3 kilowatt version. And I got trouble with the RF feedback on the line. And I'm guessing that when I get power, I start getting all kinds of weird things in the shack. So I'm wondering if I could put a RF choke up at the antenna feed point, where the balun is, if that would help.
Based on my experience, I think it definitely will.
Okay, I think I'm going to do that. I was wondering if there's any way I could use SimSmith to figure that out.
Well, I think the problem that you're experiencing is not in the model that we're using here, because it is probably due to common mode currents and imbalance on the line. You'd have to make up another model, and you could use SimSmith on that, but I'm not sure I could do that model for you. But we have plenty of experience, Keith, to know that off-center fed antennas are inherently imbalanced, and they're prone to a lot of problems with common mode currents on the outside of the transmission line, not on the inside. And I'm not saying they don't work, because they do work, but that's just one of the negatives that you have to. So I would try a good common mode choke, and you may have to put two. You may have to put one up at the top, and you may have to put one down near where the, further down on the transmission line. But I think you can knock it out to something that you can live with.
Yeah, that's what I was looking for. Actually, I have a common mode choke right now coming out of the amplifier, and it helped somewhat, but it didn't really fix it.
Yep. And
So
I think
thinking if I get another one, put it up just below the balun, it may solve the problem.
I think it'll help.
Because
I really do.
when I'm running, some of the bands will tune fine on the HF Auto Tune. I've got a Palstar, 1.8 kilowatt Palstar tuner. It works fine on some bands, but others it just can't tune.
That's right. And then the little example that I used earlier, on some of those bands it might tune, that it won't tune, you might take a piece of coax and add it to the line and see if that helps. Because I showed you how it can increase, you can increase or decrease the resistance. And we'd have to have some numbers to work on that, but could probably make some sort of a recommendation of what to do if you had some good VNA numbers. But, you know, that's the kind of thing you can do to help you solve these problems. Because that
really hit a point for me, because when I added the choke down at the amplifier, I put a 10-foot piece of coax in, and all of a sudden it started tuning that band again.
Yeah. Yeah, it works. And it's
Well,
because
thank very good. Thank you, Robbie. Excellent job tonight.
thank you. All right, other questions or comments?
Yeah, Robbie, just real quick, I'm having the same problem that Keith is having. And when I put an oscilloscope up to my antenna, I'm seeing 60 cycles. Real pretty too. And a nice clean 60 cycles. And I've got an MFJ 914, 915 Balaam at the station, and an air Balaam at the top. And I'm still wrestling with that, but that's the fun of it all.
Yeah. I'm not familiar with those. My experience has been that if you go to if you look up K9YC, K9 Yankee Charlie, he has a set of publications, and one of them has to do with making balance and RFI elimination. He gives you some good pointers there. And I have built, I use his most recent choke cookbook, which I think was published in 2018. And I've built those chokes. So that's K9YC, K9 Yankee Charlie, and his website is Audio Systems Group. He used to be a audio engineer. He's retired now. He lives in California, and look for his choke cookbook. And none of this costs anything. These are all just his publications. They're for free. They're PDFs, and you can download them from his website. If you have trouble finding one of them, get in contact with me, and I've got copies of most of that stuff, but I can definitely give you better pointers to where to find the information, and maybe can give you some ideas about how to cure some of those problems.
Thank you, Robbie.
And there's Mike, KC5MW has put out HTTP, the link to the Audio Systems Group page on the chat. Thank you. That's good. That's good. Good. Okay. Other questions?
Well, I just have a general comment, Roby.
Go right ahead, Rick.
Oh, okay. I just want to, one of the things we do as hams, it's a constant learning situation. If you don't know anything about transmission lines or antennas, you read the books and you try to put it all together, but using tools like this, SimSmith, or using EasyNeck to model antennas or model transmission lines, it helps you understand the theory. So it gives you a better fundamental background. This is just not a tool to fix something. It's also a tool that can teach you what the characteristics are and how things change and why things change, So that's probably the biggest benefit of I know this is very complex. I mean, I understand this stuff, but it's very complex. But if you back up and you read something in a book or the antenna manual and something like that, and then, like you said, build yourself a simple dipole, measure it, maybe model it in EasyNet, take those characteristics and impedance measurements and the model and put it into this, and it'll help you understand how all this stuff works together. It's not, it's not magic, man. This is all just math.
That's right.
That's why this stuff works. But what I wanted to tell you, I don't know if you're familiar with, there's a couple of programs that have been around for a long time. TL Details. Dan McGuire, he's at AC6LA, did a very similar program to this, although it's not graphical with the Smith chart, but all these calculations and everything and all the characteristics of the coaxes and stuff, that's all in there. And it's another free program. It's TL Details. Now the graphics here helps you understand, oh, I see why that's working. But after a while, you may not need the graphics, because in your head, that every half wavelength things start to repeat, and a quarter wavelength is an inversion and things like that. In the ARRL antenna handbooks years ago, Dean Straw, who was the editor, he's a smart cat, he wrote a program called TLW, and it was a transmission line program doing all this stuff. And the other thing is that he had a tuner design portion of that. You could design L networks and pi networks and stuff like that. Very similar to what you've shown here. I think that design aspect of it is better than the Smith chart itself capabilities. But TL Details and TLW are other programs that do the same thing. But I don't know. I'm going to play with this for a while. I think this may have trumped those other two.
So it's like a plumber. You got different kinds of wrenches for different kinds of situations.
Yeah.
And you can make one wrench do a certain job, but if you know what you're doing, there's another wrench that will do a better job of it.
That's right. But the big thing is that you got to have a good understanding of how all this stuff is supposed to work and how it does work, because you can come up with numbers here, and hey, this looks really good. But sometimes even in EasyNet, when you're modeling antennas, hey, those are great numbers, but they're impossible to build.
That's right.
You sort of got to know what your answer's gonna be. Not exactly, but if you know approximately what needs to be done and you do it, and you can say, okay, that looks reasonable. But if it comes out totally different, and you try to build it, then it's not gonna work. So
it's very true. In many years ago, in engineering, we used to be concerned about the new engineers that were coming out of school, because they didn't have a feel for things. They'd put numbers in a program and come out and tell me, well, it's that's 100,000 amps of fault current. I go, okay, yeah, but do you know how much that is? Do you know how much that is relative to what's normal, what's considered to be normal? There's probably not a circuit breaker on earth that's large enough to break that amount of current. No, those are great concerns. But here, I'd like to make this comment. I'm with you 100%. I think one of the best things any new ham could do would be to take EasyNet and go through those antenna models, those preliminary ones in the Get to Understand EasyNet section, and take a simple dipole and change its elevation, build it for a certain frequency, put it close to the ground, and raise it up. And each time you raise it a certain number of feet, look at its pattern and look at its impedance and all that stuff. And it will show you so much about what to expect out of an antenna. I help people and they say, well, what if I want to, I'm really concerned because it's off at a little bit of an angle. Okay. I'll model that stuff at an angle and it don't make a whole lot of difference. That helps. It's the same thing you're talking about. It really helps you get a feel for what to expect or how these things are supposed to behave. And these models are sophisticated enough that they on the negative side, they will get you into a trap. They will get you into things that won't work. But for the most part, they're pretty good. They give you fairly reasonable data, and it's the best way. So for myself working with new engineers, what I learned from them was in my engineering school, a huge portion of my time was spent teaching me to be good enough to do the calculations that I talked about early in this presentation, and to do them accurately enough and correct enough in order to get reasonable answers. And the theory part behind it was kind of almost second to being able to handle the math. Well, now we have the math is being taken care of with these simulation programs, with SimSmith, with EasyNet, with that sort of thing. Now those guys can focus on how the system works, and they don't have to be so buried into the details of doing all the calculations. So they learn more than I did. They were able to expand their horizons beyond what I was able to, because I had to spend so much of my time, beating the math to death. Okay.
Yeah,
I got just a little bit more, but go ahead. I got a little bit more I want to show you guys, but not on SimSmith, but I've got another sheet I want to show you. So other comments, or if you want me to go back, I'll go back. I'll answer, do what I can. Okay, I got one more thing to show you. This is this is what I call my credits, my references. So I drew this information, the slides, from the Basics of Smith Charts by Alan Wolke, W2AEW. I got some of this stuff from RF Engineering, Basic Concepts of the Smith Chart. I got a little bit more of it from Impedance Massing and Smith Charts by John Staples. If you don't own an ARRL antenna handbook, go buy one. It's for hands. It's one of the best things you'll ever do. It addresses all the stuff I've talked about here and more, not in the detail, but you now have a tool, just like Rick was saying, you now have a tool to try to learn more about antennas and about how things work. SimSmith for Interactive Circuit Analysis, which is what SimSmith's official name is, by Ward Harriman, and Larry Benko, W0QE. And he is a retired electrical engineer who, amongst other things, does SimSmith instructional videos on YouTube. These guys right here are really good. As far as learning this and how to use it, there are literally tens of hours of YouTube videos on this subject. And Larry Benko is excellent. And he has a beginner series, an intermediate series, and an advanced series. And it is very interesting to be able to listen to him. And the only thing I will caution you with, or caution you about, is taking any of the YouTube stuff from either AE6TY or W0QE. Is what they generally did was take the version of SimSmith that was the most recent at the time they made the video and explained how to do it using that version. So this program has grown rapidly. So there's some differences. Basically, it's the same, but there are some features in a later version that did not exist in an earlier version. you know, that sort of thing. So that's the only kind of difficulty that I would like to point out that you need to be aware of when doing that. In fact, both of them say that whenever you do their preliminary introductory series, they'll tell you just what I said here. So, but it's something to it's something to it's a great way to learn.
Hey, Roby, that second reference, RF engineering, is that a publication? You said
Yeah.
June 2010.
Yes.
What is that publication?
I got a slide, one of those slides out of it, but it's really the heavy math treatment of the Smith chart. It's about the how the Smith, if I remember correctly, it's about how the Smith charts form. That it's a complex reflection coefficient graph.
Right. Okay.
I remember, and I got tired of looking at it, but there was some good information in it.
Okay. All
you know,
right.
I'm not.
I won't go there. Never mind.
I'm not trying to be a wizard, you know. I'm trying to be moderately proficient at this. So
no, I understand. Yep. You done good.
Thank you. Okay, guys. That's my story.
That was a great story, Roby.
Can I make one other statement? I forgot. There's something you asked that I had not addressed yet.
Go ahead.
Okay, so sometimes, so you understand what the Smith chart display is. It's reactances and resistances on a complex graph. Sometimes whenever you look at a transistor or some other component that has characteristics that depend on frequency, they will plot those over a frequency range and put them on a Smith chart, just because it's such a good way to show that. And so a lot of times you will see a Smith chart plot showing impedance values over a frequency range, just because it's a good display tool. The other thing is, on your vector network analyzer, they use the Smith chart because it's such a good way to display the data. And I think I demonstrated for you that how you get that circular map, that circular one that you see if you use your VNA and you use it over a certain frequency range, you'll see the spiral. And that's due to the impact of the fact that your load impedance is probably changing with frequency, and the length of your transmission line is changing with frequency. Electrical length of your transmission line is changing with frequency. And that's what gives you those big circular plots on your VNA.
Okay, well, thank you very much, Roby. It's fascinating. I can't wait to try to apply that in real life. It's probably to that new shortened 80-meter dipole.
Cool.
If I can figure out a way to put the traps in there. Anyway, thank you very much. The presentation is going to be, I have to render it tonight off of this recording, and it'll be up on the TDXS website in another day or two. So thanks for attending. I'm sure you agree with me that this is a great talk, and we'll look forward to seeing you again next month.
Thank you, Roby, and thank you, Doug and Roby.
You're welcome.
Yeah, thank you, Roby. Well done.
Yes,
Well
thank
done.
you very much.
Thank you, Rob. Very much appreciated.
Okay, good night all.
All right, good night.
Good night, Doug.
Adios.